So welcome to day 17. Danny's here, and we're going to talk about sequences today, arithmetic, geometric, and alternating sequences. We're also going to talk about factorial, which you've probably seen, but you may not have seen the recursive definition that we're going to use. I want to point you to a short video that's going to be made available tomorrow in our YouTube 263 discrete short videos playlist, and that will cover N choose R. So you can watch that later in the weekend. So there's a little do now quiz, even though it's not graded. And the quiz is this. It's supposed to warm us up to think about sequences. Find the next three terms of each sequence. So the first sequence starts like this: 2, 5, 8, 11, 14, and then dot, dot, dot. See if you can figure out what the next three terms of that sequence are. If you can see a pattern. And the second one is 3, -9, +27, -81. Keep on going. So do you see a pattern, Danny? And if you don't want me to call on you specifically, since you're the only one here, just say so, and that's fine.
Oh, gotcha. Yeah, I see patterns in both.
Okay, what's going on with this first one?
So the first one, you keep adding 3 to the next term.
Exactly. So what are the next three terms? You tell me and I'll write them down.
Be 17 and 20
Yep,
and 23.
very nice. Nicely done. So we're seeing enough of the pattern to keep going. How about in this second sequence? Do you see a pattern going on with that one?
Uh, yeah, I think it's each term is multiplied by -3.
That's exactly right. So the next term would be a +243, and the next term is a -729, just in case you don't have your calculator handy.
Gotcha.
And yep, and then the next term is +2187. And these are examples of arithmetic and geometric sequences. An arithmetic sequence is a sequence where we add something over and over and over again to get subsequent terms. And a geometric sequence is a sequence where we multiply by something over and over and over to get subsequent terms. So before we look at some more examples, let's just go ahead and get a formal definition of a sequence. We are still in section 5.1. Section 5.1 turns out to be fairly meaty. So, talking about sequences now. And our definition goes like this. A sequence, often denoted by, and it looks like a set, because it is, but it's a set of a specific type. So we put set brackets, and then something like A sub I, or it could be B sub K, depending upon what we're using to name the terms. But the point is, this denotes a sequence, and what a sequence is a list, we're defining sequence, of terms, each of which has a position in the list. So it's different from the kinds of sets that we talked about at the beginning of the semester, where the order of the elements didn't matter at all. The order is very important when we list the elements of a sequence or the terms of a sequence. And the indexing number, and that's denoted by this subscript, the indexing number of a term is the subscript that indicates the relative position of that term. So it's the relative position of that term in the list. And I mean relative to the other terms. And the indexing numbers increment by +1, just like with our sum and product notation. The indexing numbers increment by +1 from term, say, a sub k to the next term, which we'll call, of course, a sub k plus 1. So for the first time, we're going to actually be doing arithmetic inside subscripts. So here's an example of just a generic looking sequence. And here, the indexing numbers are these subscripts. Okay, so these are the indexing numbers. I think I've got some good video settings finally. I had to futz around with them when my computer died, and I think this is actually better. And then these are called the term names. Each term has a name, and that includes the indexing number. And it turns out the indexing does not have to start at 1, okay? It could start at 0 or some other number. So the indexing does not have to start, does not have to start at I equal 1. It could be a different indexing start, and we'll see examples of that. Okay, so now let's define an arithmetic sequence, which is of the sort that we saw here in part A, where we add something over and over. So arithmetic and geometric sequences, and it looks like arithmetic, but it's actually pronounced arithmetic. Arithmetic and geometric sequences. Bottom at this range. So here's our definition for an arithmetic sequence. An arithmetic sequence curly brackets a sub I is, say, a0, a1, a2, dot, dot, dot. Now, when I say a0, naught, N-O-U-G-H-T, is an old-timey word for 0. It means nothing. So instead of saying a sub 0, I usually say a0 has an initial term, and that's the a0 term. And say a0. And a common difference. And that's what we saw being added over and over, that common difference, denoted by D. Such that we get that a0 is the initial term. I think in the notes that are posted, this is in red, but I think it shows up better in green here on camera. And then a sub k plus 1 is a sub k plus d. And this works for k greater than or equal to 0. So let's just check that that makes sense for it to work for k greater than or equal to 0. When k is equal to 0, if we put 0 in here, this term is a sub 0 plus 1. Of course, that's just a sub 1. And that equals a sub 0 plus d. And if it's k equals 1, then this says a sub 1 plus 1, or a sub 2, is equal to a sub 1 plus d, and so on and so forth. It just keeps going forever after. Does that make sense? So let's look at an example. We're going to find the initial term and the common difference. D for this sequence. And it's going to be the very same sequence that we've already seen. So this is just going to seem a little silly, but why not use it? It works perfectly well. 2 5, 8, 11, 14, So one thing I want to show you is notice, even though it's not written, we're only told that the first term starts with a sub 0, it's indexed with 0. That means this term 5 is called a sub 1, 8 is a sub 2, 11 is a sub 3, 14 is a sub 4, and so on and so forth. So we understand that much. Here, we are told the indexing starts at 0. Okay, sometimes we'll be told where the indexing starts, and sometimes we won't be told. So the solution here is, of course, the initial term is just this term that was given first. It's a naught equals 2. And the common difference, of course, you figure it out, is that quantity that's getting added over and over, and that's d equals 3. Now we have a formula for the general term of an arithmetic sequence. Formula for the general term, a sub n, for an arithmetic sequence. Where that sequence looks like a naught, a 1, a 2, having common difference d. And that formula goes like this. It says, hey, if you want to find the term a sub n, the way you get that is you start with the initial term, a sub 0, and we're going to add d over and over again to get up to n. So we add n copies of d. So that formula works for n greater than or equal to 0. It even works for the initial term. Let's check this. When n is equal to 0, this formula says a sub 0 is equal to a sub 0 plus d times 0. In other words, we haven't added any copies of d yet. In other words, a sub 0 is just equal to a sub 0. When n is 1, well, a sub 1 is equal to a sub n plus 1 copy of d. When n is 2, a sub 2 is equal to a sub n plus d times 2. In other words, we've added d twice to get to a sub 2, and so on and so forth. So here's an example. I'll call it 1b, and you can do this later. Consider this sequence. A naught is 5, then 15, 25, 35, 45, So for part A of this do later, find the initial term and the common difference. And then write the specific formula for this sequence for the general term. So write the specific formula for the general term of this particular sequence. Okay. We could even add a part C, and that part C would be to find a sub 99 or something like that. You can just use the formula and find that. Now, a geometric sequence is the next kind of sequence we want to define. a geometric sequence say a sub I, which is a sub 0, a naught, a1, a2, dot, 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 has an initial term, a naught, and a common ratio. Instead of a common difference, we have a common ratio denoted by R, such that the way the sequence looks is a naught is the initial term, and to get a sub k plus 1, well, that's equal to the term before, a sub k, times R. And this works for k greater than or equal to 0. So this is the way that we generate the terms of a geometric sequence. We multiply by R. So we're going to look at an example too that's slightly easier than the example we saw in our little quiz, because it was a sort of complicated geometric sequence where we were multiplying by a negative common ratio. But here, let's find the initial term and the common ratio, R, for this sequence. A naught is 1, 2, 4, 8, 16, dot, dot, dot. And it's easy to see what's going on here. We're multiplying by 2 to get subsequent terms. And we're starting at 1. So the initial term, a naught, is 1. And the common ratio, R, is 2. We have a formula for the general term a sub n of a geometric sequence. So here's the formula for the general term. A sub n for a geometric sequence a naught, a1, a2, dot, 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 having common ratio R. I'm saying all this stuff over and over because I don't want there to be any confusion, but there really couldn't be. Right? And that formula is, hey, to get to a sub n, what do? Well, we start at a naught, and then we multiply by R over and over again. But the mathematics of iterated multiplication is exponentiation. So we raise R to the exponent n. So rather than adding d n times, we multiply by R n times. And this works for n greater than or equal to 0. So here's a little do later, just to help you feel comfortable with geometric sequences. Find the initial term and the common ratio R. And the formula for the general term. We'll do it all at one fell swoop. A sub n for this sequence. A naught is 1, then 1/5, 1 over 25, 1 over 125, 1 over 625, and so on and so forth. Any questions?
Nope, I'm good so far.
So you might have been wondering, why do we call this R a common ratio? Because a ratio is usually when we've got something over something, we're dividing something by something. But here we're not dividing, we're multiplying. And why do we call the common difference a common difference when we're adding it instead of subtracting it? Why don't we call it the common summand or the common factor? Well, the reason for that is because it gives us information about the relationship between subsequent terms, consecutive terms. Why do we call D the common difference and R the common ratio? Well, we can look at these side by side and we can see what's going on. In an arithmetic sequence, versus what's going on in a geometric sequence. If we think about k being greater than or equal to 0, if we look at a sub k plus 1, we have a formula that a sub k plus 1 is a sub k plus the common difference d. But if we subtract a sub k from both sides of this equation, then a sub k plus 1 minus a sub k always turns out to be d, no matter what k you pick, 0 or larger. This is a sub 1. If when k is 0, a sub 1 minus a sub 0 is d. When k is 1, it says a sub 2 minus a sub 1 is d. So this difference is common between any two consecutive terms. It's the same for the geometric sequence. If we take a sub k plus 1 and divide it by a sub k, how did I get that? Well, I'm looking at this formula that a sub k plus 1 is a sub k times r. So if we take both sides of this formula and divide by a sub k, then on the left side we have the ratio a sub k plus 1 divided by a sub k. And of course, on the right side, when we divide by a sub k, that cancels, and we're just left with r. So that shows why it makes sense to call d and r the common difference in the common ratio rather than the common summand and the common product. So here's a do later, which can help you figure out if a particular sequence really is geometric or arithmetic. For part 1, check a sub k plus 1 minus a sub k for k equals 0, 1, 2. Yeah, that's enough for 0, 1, and 2. Where you can do 2 of them. In the first sequence, a naught is 15, 21, 27, 33, dot, dot, dot. For the second sequence, a naught is 15, then 21, 28, 35, dot, dot, dot. See if you can detect which of these is an arithmetic sequence. And in fact, if one of these is not an arithmetic sequence and one of them isn't, then dot, dot, dot doesn't actually even make good sense. Well, let's do the same thing for geometric sequence. Check a sub k plus 1 divided by a sub k for k equals 0, 1, and 2, where, well, the first one can be a naught is 5, 25, 125, 625. I think you can see right away that that's going to work out. But this one, a naught is 1, 1/2, 1/4, 1/6. And see, which of these is a geometric sequence. Because if you don't have the common ratio work out for every pair of consecutive terms, then it's not going to be what you think it is. So that brings us to the next topic for the evening, which is alternating sequences, because in our Do Now quiz, we did see what's called an alternating sequence, and that's a sequence in which the terms flip their signs. They alternate plus minus, or minus plus minus plus. Here's the definition. An alternating sequence is a sequence in which the terms alternate signs. It's that simple. And there's a trick for making that happen mathematically. So let's discuss a possible formula for the general term of this sequence. And I'm not going to give the original indexing number because that might be something that's left up to us. And in fact, you have enough programming experience to know that sometimes you may not want to initialize something at 0, like an indexing number. Sometimes it might not matter, but sometimes it might. So what about this sequence? It's just the simplest alternating sequence of all. 1, -1, 1, -1, 1. And as you know, this does not converge. You've got enough experience to know that. So let's look at two different solutions. Sorry about that. These solutions are going to hinge on how we decide to initialize the indexing. So let's suppose we decide to start the indexing at k equals 0. Okay? In other words, this sequence looks like a naught is 1, and then -1 is what we would call a 1. +1 is a 2. -1 is a 3. +1 is a 4, and so on and so forth. Okay? How can we use the indexing number to help us get the correct sign for each term? That's the question we want to be asking, because we need to connect the indexing number to the formula for the term. So how can we use the indexing number to help us get the correct sign for each term? Now, in this example, I want to make clear that I'm talking about in this example. If we look at the terms that are positive, well, see, the indexing numbers for the positive terms are 0, 2, and 4, right? Those are the terms that are positive, positive 1. So in this example, if the indexing number is even, like 0, 2, 4, 6 would be the next positive one. So if the indexing number is even, the term is plus 1. But if we look at the terms that are negative, the indexing number is 1 and 3. And of course, a sub 5 would be negative 1. So 1, 3, 5, 7. It looks like if the indexing number is odd, then the term is negative 1. And that's exactly what's going on in this particular example. And it turns out if the indexing number is odd, the term is negative 1. We can use that because we can connect these indexing numbers with the exponent k that will give us the correct sign. So our job is to connect the indexing number to the exponent k in negative 1 raised to the k, because this is our key to getting alternating signs. If you raise negative 1 to an even integer power, you get positive 1, like negative 1 to the 0 is positive 1, because any real number raised to the 0 is positive 1, including a negative real number, except 0. We don't raise 0 to the 0, but any non-zero real number raised to the 0 is going to be positive. So a sub 0, which is positive 1, that is negative 1 raised to the 0. And a sub 1, now a sub 1 is negative 1. Well, we want to connect that indexing number 1 somehow to the formula, and it's going to work out perfectly because in this example, which I designed this way, if we start our indexing at 0, then the even index terms are positive and the odd index terms are negative, and we can just use the indexing number as the power. Yeah. So it works, for 2 and 3 and 4, because we want to get positive 1 and then negative 1 and then positive 1. But that's what we'll get if we raise negative 1 to the 2 or the 3 or the 4. We get positive, negative, positive. So our answer in this case, where we have chosen to start with k equals 0 as our first indexing number, a sub n, in fact, is negative 1 to the n for n greater than or equal to 0. When we do give a formula for the general term, we have got to be always sure and include the information about where the indexing starts. So be sure and state where the indexing begins in the formula. Otherwise, if you just say a sub n equals negative 1 to the n, it might not be this sequence, you see. You have to tell the reader where that indexing starts. It's just like, any kind of definition that we have, it usually has more than one part. But what if we decide, instead of starting the indexing at k equals 0, What if we decide to start the indexing at k equals 1? We might have good reasons for doing that. Let's just suppose that we want to start the indexing at k equals 1, and let's see what the formula would look like in that case. So example 3. So let's suppose this is solution 2. Let's suppose we start the indexing at k equals 1. So in other words, a sub 1 is the number positive 1, and then the negative 1 will be a sub 2, 1 will be a sub 3, negative 1 will be a sub 4, 1 will be a sub 5. Let's go ahead and write these. So this is a sub 2, this is a sub 3, this is a sub 4, this is a sub 5. Okay. So if we decide to do that, we still have the same job where we have to connect the indexing to the exponent. But now, the even indexed terms are the negative terms, whereas the odd indexed terms, like 1, 3, 5, are the positive terms. So as we try to analyze it, we have to make an adjustment and realize that we're starting at 1, then there's 2, 3, 4, and 5, but we want to get positive 1, negative 1, positive 1, negative 1, positive 1. And it's not going to work out if we raise negative 1 to the indexing number of the term. So the trick is to say, hey, I can take the indexing number 1, which would make this negative 1, which isn't what I want. We want positive 1. We can just add 1 to that, and that changes that 1 into 1 plus 1, or 2. And that's the correct exponent, because when we square negative 1, of course we get positive 1. So if we just take each indexing number and add 1, it'll correct the parity so that we'll get the correct sign. And in this case, our general term is going to have a different formula. And we can use a sub n, or we can use a sub k, it doesn't matter. Do you see what the formula is? A sub k is going to be equal to negative 1 raised to the k plus 1. And this is for k greater than or equal to 1. Again, we're going to include where the indexing starts so that this formula really gives us the sequence that we want. Let's do another one. Let's find a formula for the general term and this time I'm going to change the name, B sub n. So we'll use some B's for a while. In fact, A's, B's, C's, D's, E's, and F's are all used to name sequence terms for this sequence. And this is a sequence of B's, so I'll say B sub i's. 1/2, negative 1/4, 1/8, negative 1/16, 1/32, dot, dot, dot. So we can play the same kind of game that we played before, where we decide how do we want to start the indexing, right? We could start the indexing at 0, or we could start it at 1. So let's just quickly go through a little analysis. Solution 1, solution 2 of what we would get with those choices. Here, if we start at I equal 0, you can call it I, you can call it K, you can call it N, it doesn't matter. Then let's take a look. So that means B sub 0 is 1/2, positive 1/2. So we know we're going to have an alternating sign. So we know we're going to have to deal with -1 raised to something. And it also looks like the common ratio has a magnitude of 1/2. Common ratio is actually -1/2. So B sub 0 is -1. Well, we don't want it to be negative, but if we raise that to the 0, that becomes positive. But we want to raise 1/2 to the 1, you see. So the -1 and the 1/2 actually have different exponents. Let's look and see if we can see the general pattern. Okay, so this -1/4 would be B sub 1. Well, we want it to be negative. So we'll keep the 1 as the exponent on the -1, but it needs to have a magnitude of 1/4. So that means we can add 1 to 1 and square 1/2, and that gives us -1/4. And I think you can see that if we just consistently apply this pattern where we use the indexing number as the power on the -1, that will work out to give us the correct sign. But then the power on the 1/2 just needs to be 1 bigger than the indexing number so that we get, if this is a B0, this is B1, B2 needs to be 1/2 cubed. So that's 1 greater than 2. And 1/16 is 1/2 to the 4th. So the 4 is 1 greater than the 3, and so on and so forth. So I think you can see that our general formula looks like, here we'll put the indexing information first. For n greater than or equal to 0, because we're indicating we're starting with our first indexing B 0, B sub n is -1 to the n times 1/2 to the n plus 1. Let's make sure that people can see that. I'll scooch this over just a little bit. -1 to the n and 1/2 to the n plus 1. There we go. But what if we start at I equal 1? There might even be good legitimate reasons for you to start at I equal 2, in which case you could sort that out. But if we start the indexing at I equals 1, that means this first term, 1/2, is B sub 1. And it needs to be positive. But if I raise -1 to the 1, that's not going to be right. But if I square it, if I add 1 to 1, then this is positive. Here, the 1/2 being raised to the 1 is the correct magnitude. So if you just look through this, it looks like, since we want the odd index terms like B1, B3, B5 to be positive, we know we can't use the odd index. We have to add 1. Oops, should be a 3 because we want the even ones. So we want 4 here, and we want 6 here, and that'll give the right sign. And then if this is B1, then B2 is -1/4. B4 is -1/16. So again, we don't want to get a positive, so we have to raise the -1/2 to the power that's going to flip the parity. So just add 1. But it looks like for all of these, the correct exponent to give the magnitude, the number part, is going to be just the exponent of the indexing number. And that's right, because if this is B1, that's 1/2 to the 1. If this is B2, that's -1/2 squared. If this is B3, that's positive 1/2 cubed. And then it'd be -1/2 to the 4th and positive 1/2 to the 5th. So for n greater than or equal to 1, our formula B sub n is -1 to the n plus 1 times 1/2 to the n. So depending upon what you're trying to do, you'll get different formulas. Questions? Our last topic for the evening is factorial. And you've probably heard about factorial. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. That sort of thing. But there actually is a recursive definition for factorial. And here is the definition. It's for any integer n greater than or equal to 1. Okay, now we're going to actually start with 0 factorial. That's not one of our n's. There's no n here. 0 factorial is defined to be 1. It's not 0. If 0 factorial was 0, then when we performed factorial, we'd always wind up multiplying by 0 at the end, and everything would wind up being 0, and that wouldn't be any fun. But for n greater than or equal to 1, we define n factorial to be n times the quantity n minus 1 factorial. This is what we call a recursive definition, because we're defining something for n in terms of things that happened earlier, in terms of what happened with n minus 1. So it's like to go ahead, we have to look behind. To look forward, we look backwards. That's the nature of a recursive definition. This is our first recursive definition of the semester. So here's an example. Let's find n factorial for 0 less than or equal to n less than or equal to 5. We're going to do all of them. We're going to get some practice. Here's our solution. We'll just list them. So for n equals 0, for n equal 1, for n equal 2, for n equal 3, for n equal 4, and for n equal 5, we will calculate n factorial. And we are going to use the recursive definition, at least for a little while, because there are good reasons to understand it. So when n is 0, our formula says, hey, 0 factorial is 1. So that's it for n equals 0. Now, when n is 1, we want to find 1 factorial. So we start to use the recurrence relation. This part's called the recurrence relation. It says 1 factorial is equal to 1 times the quantity 1 minus 1 factorialized. Well, that's 1 times 1 minus 1, of course, is 0 factorial. But we know that 0 factorial is 1, so this is 1 times 1, which is also 1. Seems like a lot of work to get 1, but there's good reason to do this practice. Okay, when n is 2, we're still going to use the recurrence relation. 2 factorial is equal to 2 times 2 minus 1 factorial. So that's 2 times 1 factorial. Well, 1 factorial is 1, so it's 2 times 1, or 2. We'll do one more the long way. 3 factorial, okay? So n is 3. It's equal to 3 times 3 minus 1 factorial. Oh, well, that's 3 times 2 factorial. Well, we just learned that 2 factorial is 2, so this is 3 times 2, or 6. So it starts to look familiar. I think that everybody's probably getting the drift that when we want to do a calculation for n factorial, it's n, here n is 4, times the integer right before 4, which is 3 factorialized. So we won't keep writing 4 minus 1, and 5 minus 1. We'll just write 4 times 3 factorial. Well, that's 4 times, 3 factorial was 6, and that's 24. Finally, 5 factorial. We'll do one more. It's 5 times 4 factorial. Well, that's 5 times, 24. That was what 4 factorial was. And that's 120. Okay, so this is the way that it goes. Let's look at an example and let's simplify as far as possible. Let's play the game. Here we go. 9 factorial divided by 6 factorial times 3 factorial. All right, so we want to simplify this. 9 is the larger number, and we know we can expand this. We know this actually means 9 times 8 factorial, but 8 factorial is 8 times 7 factorial, and 7 factorial is 7 times 6 factorial. So hang on, 6 factorial. There's one down here. So we can write 9 factorial as 9 times 8 times 7 times 6, and we could write times 5 times 4 times 3 times 2 times 1, but why don't we just write 6 factorial here, because that's what it is. And then you can see why we stop there. We can cancel the 6 factorial upstairs with the 6 factorial in the denominator, and now we've got 9 times 8 times 7 up top, and we've got 3 times 2 times 1 on the bottom. Well, this is easy enough to do in our heads. The 3 can cancel with the 9, right? Leaving a factor of 3 up top. And the 2 can cancel with the 8, leaving a 4 up top. So suddenly all we've got left on the bottom is 1, and we've got 3 times 4 times 7 up top. And of course, that's 12 times 7, or 84. Let's do another one. N plus 1 quantity factorial divided by n minus 1 quantity factorial. This is when this definition really helps. That's what we need, the definition now. The thing to understand about these integers, and they are integers, we assume that this is defined. This is for n greater than or equal to 1, okay? Because when n is 1, this denominator would be 1 minus 1, or 0 factorial, and that's okay. 0 factorial is okay, because 0 factorial isn't 0, it's 1. It's okay to have 0 factorial, but we wouldn't be able to use this expression for n equals 0, because if we put a 0 in here, we'd have -1 factorial, and that's not defined. Okay, now, my point is this. If we look at a number line, n plus 1 could be here, all right? Now, the integer just before n plus 1, of course, is n, because it's 1 less. And the integer before that would be n minus 1. And you could keep going. If you kept going this way, then there would be n minus 2 and n minus 3. If we kept going this way, there would be an n plus 2. At some point, you've got enough of these to see what's going on. N plus 1 is bigger than n minus 1. So this is the one we're going to expand. So what we understand is, okay, what is n plus 1 factorial? It's n plus 1 times the integer before, which is n, times the integer before that, which is n minus 1, times everything down below that. Oh, that's factorial. And that's why we stop there, because we can cancel the n minus 1 factorial up top with the n minus 1 factorial downstairs. And then our simplified expression is simply n plus 1 times n. I'll give you some do later problems. Simplify completely. And again, I'm just going to put my plug in here for the short video that's going to get posted tomorrow on N choose R. And believe me, you want to learn N choose R, because it's going to help you if you want to expand a big old binomial. So here's our do later, example 8. A, simplify completely. N plus 2 factorial divided by n factorial. And B, another practice problem, would be n minus 1 factorial divided by n factorial. So don't be fooled. Just because these first two examples have the bigger number up top, it doesn't mean that has to be that way, right? Here, the larger number is actually in factorial. You always want to expand the larger number that's getting factorialized so that you will eventually see the smaller number factorialized, and then you can cancel those factors. All right, well, this is actually a shorter than usual lecture. Yay, we got through this material in less than an hour. And that's good because that saves you 15 minutes later in the weekend to enjoy our second video. I want to thank Danny for coming in and saying hi to me and being here in the room. So I wasn't just talking to myself. Have a great weekend, everybody.
See you, Professor.
See you, Danny. Do you have any questions?
Uh, actually, I think everything makes sense.
Oh, that's the plan. The plan is to make it seem so easy it actually makes sense.
All
All right. Thanks a lot for playing.
right. See
Bye.
you.
Bye.